With that background of our history in place, I'm going to take you through today this list of things. So we're going to talk about the motivation, game physics, so what we want to keep our attitude about nowadays, in the early days, is to ask ourselves, as we get more sophisticated versions of our game, our simulation, let's identify the game physics without trying to work too hard in the beginning to force it to correlate to physically realistic physics. Hilbert space, probability-weighted Hilbert space, quantum clock, empire wave, absolute space-time proportionality and relativity, the statistics of c, speed of light, EM fields as a tensor product of S1, S2, and the universality of this concept of S1, S2, charge, polarity, and spin in the game physics of our empire wave, the geodesic behaviors of their statistical random walk movements, the 1 over r squared nature of the empire wave fields, discrete quantum fields, the idea that there is no position in our game because a particle exists only over a quantity of graph inflation states. I'll explain that later. The S-index idea, the idea of a function versus a unitary evolution, the idea of special functions or algorithms that allow you to dial in to some state in the evolution or the series, if it's a series of numbers. The coincidence of the form of anyons used in quantum statistics for topological phases of matter and our form called the Fibonacci matching rules being identical. Mass, momentum, and inertia, how deltas to m equal a delta in a d over t. This is m as in mass. The fact that there are an infinite number of directions that a Fibonacci chain takes in an infinite quasi-crystal. 3 families and 3 generations of mass, photons, energy, gravity. The axis has no drop and uses exponentially fewer center emperors, geodesics in gravity, quanta of curvature, why average curvature in the universe is flat and the sum of squares law, why only attractive as gravity, why the equivalency principle, G relationship to phi. I'll figure out what that BH means. The ADS CFT, huh? Oh, black hole. Yeah, black hole singularity. ADS CFT correspondence and the shell model hyperbolic asymptote. And then the algebra problem that is nearly solved, I believe, of my 2-year-old AB equals P problem, which I'll explain what my problem is, and how that relates to matrix mathematics, and why you don't need to do projective geometry, why you don't need to follow through with the trigonometry to have a quasi-crystal, and how that relates to E9. So as motivation, I kind of said what the motivation is by telling you the story of how we started QGR. But one thing to add to that is, my interest is to know why for everything. So gauge symmetry physics is not enough to satisfy me, my desire. I believe that if we can create first principles simulation physics that are physically realistic, that it will, by definition, spit out and define gauge symmetry equations. But it's more important to me to understand why Planck's constant has the value it has, why the fine structure constant has the value it has, and so on. And so that is a very audacious goal, right? But you should understand that that's what makes us unusual. In fact, I'm not aware of any other quantum gravity groups that have the intention to know fundamental constants from mathematical first principles. I'm not saying that they don't exist. I just am not familiar with their work. So that's a big part of my motivation. But the biggest part of my motivation is really what happened to me at Singularity University, where I would call it love. Because either you're doing things like donating money without anybody knowing, you know? Like, why would you do that? You're going to lose your money and nobody's going to know. So you're not going to get any adulation or appreciation from anybody, and you're going to have less money, less stuff for yourself. So I would call that love. And so it seemed like these people who inspired me at Singularity University wanted to do what they wanted to do out of love, service, just service, you know. And so at first, I mean, a big part of my motivation is my own selfish curiosity, because who wouldn't want to be on a treasure hunt to discover what is arguably the deepest questions of all of reality, which is, what is reality exactly and how does it work, and what does consciousness have to do with it? Like, that's it. That covers the deepest questions of religion, philosophy, and science, right? So, so that's selfish and fun and stuff, but it's not as important as my other motivation, which is service, aka love. So I invite you all to explore your motivation and the sense of love, because I know all of you have love and service in your heart, but the more you kind of acknowledge it and say, hey, I'm coming to work out of love and service, I don't know, the more fun it makes it. It fuels you. Game physics is what I just explained a second ago. So now I'll explain Hilbert space. So when we start with a finite or infinite possibility space of points called the QSN. And you can think of the QSN with edges connected, or you can think of them, if you prefer, as just points without edges. And we set that at phi 1. That's the beginning. You can think of that as kind of like the Planck scale, or the minimal pixels of distance. And then what we do is we do inflations, and let's say the simplest inflation is at 1 power of the power series up at phi 2. And so I always draw this as with the symbolism that I call WP and WB and their relationships. So WB on the point set in any dimension is stands for boundary. So we have a boundary window of any size that you please, as long as it's not infinite. So again, it doesn't matter the size. And so for any size boundary, you project any points that are captured in the boundary down any number of dimensions. So in this case, we're going to go from 2D to 1D. So we'll place all of the points that are trapped in this boundary window B into the one-dimensional projective space. And then we're going to call this space here, our possibility space. So our possibility space of the QSN is generated by a boundary window B in 8 dimensions that has a certain thickness. And really can be any thickness. So then we have a smaller window, a window of lesser height. And so let's say that this is a finite length of window B. So we take the same length of a window P, and we say, all right, let's say I take a window P that has 0 thickness, right? 0 thickness. But it can be any thickness less than B. And so since I had n points in B, so I had n points in B, which places n points in my possibility space. And now I have my window P, and I'm going to center my window P on, or I'm going to make my window P coincident with one of the points that is, one of the n points that is within B. So obviously, because it's an irrational slope, B must be irrationally sloped relative to the root vectors of your lattice. Because of that irrationality and because of the finite length, then if I've selected this or any other point to be coincident with my 0-dimensional window P, then no other point can be coincident with it. So this becomes my center emperor. And then that, let's say, correlates to this. So in this case, when I project this upon the possibility space, I turn all these guys off, these and these off. Now, if I were to make a window P that's thicker, I could select the thickness such that if this slope were such that it would generate a Fibonacci chain as my possibility space, and then I would know what thickness I need to make my window P relative to window B, such that I can do my inflations. Remember, I set this as phi 1, and that's my window B, and I want my window P to be inflating at phi 2. So I set my P thickness to that, and then I say, okay, I can only have one and only one point at the center of the height of window P. So now that's my center emperor. So now from doing it that way, now I'm turning off half the points. So it becomes binary. So I'm turning off half the points at phi 2 in my possibility space. So we can say that one's on, that one's on, that one's on. And so it now becomes a quasi-crystal inflated to the scale of phi 2. But I say, well, it looks like there's several choices that I can make, right? Let's say that I can go up to here, right? Go up to here, so there might be some points up here that I can't get to be the center. So I have some number of points m now that I can choose to be the center emperor. And the point of this is that the quantity of center emperors that I can pick is exactly the quantity of possible inflations at phi 2 that are possible on this space. And so that quantity is m. So then I can say, all right, is that formally a Hilbert space? So because it's a point space where I can put a binary label on a point as being on or off, then I can call this a Hilbert space. As obviously it's not a statistically weighted Hilbert space because all of them have the same weighting at this point because there's nothing to determine the probabilities. So now we can talk about the probabilities for random walks. So we have m as a random walk. In other words, I go through in any order that I choose. I take the m different inflations and I just choose to order them in some animation, right? Let's say if m is 10, right? Let's say there are 10 ways I can inflate this. So I have m factorial animations, or random walk or action animations I can make in this one-dimensional space. So 10 factorial is about 3.6 million. So I have 3.6 million animations that I can make. Most of them won't have quasi-particles. Most of them will be so chaotic that you can't pick up any coherent ruled surface over time. Some of them will be quasi-particles moving from right to left. Some will be moving from left to right. Some will move from left halfway up and then go back 1/4 and then go up. There'll be all these coherent patterns. And some can have multiple quasi-particles moving, right? So if you take this up to higher dimensions, like 3-dimensional quasi-crystals, then the vast majority of your orderings of your possible inflations are noise, just nice-looking, smooth, homogeneous noise. And some of them are quasi-particle animations where there's only one quasi-particle in the whole system. Others have 2, others have 3. And they can become very complicated if you do it the way we're trying to do it, where we're building complicated phazon animations that have ruled surfaces that are rich. And then we introduce a game rule, which is, as we know, the PEL. So to talk about, so this is review. I mean, obviously you guys know pretty much a lot of what I'm saying today, and other stuff is going to be new to most of you. So when we introduce the PEL, okay, we can evolve to a statistically weighted Hilbert space. And we're going to talk about building out an S-index really slow and methodically today, and talk about how the S-index is an analog of the unitary evolution for the random walks of particles in our game, the PEL game, Principle of Efficient Language. And you'll get different random walks that have different probabilities. So your random walks can be spin changes, they can be directional changes, okay? They can be accelerations. So all of these different possible walks and interactions or evolutions are all encoded in some number, which is n factorial, right? However many inflations there can be, then the total amount of patterns that can be made are defined in this Hilbert space n factorial. And then we apply the PEL and the game rules, and then we start building out statistical indices called the S-index, and then that creates a statistically weighted Hilbert space. So, for most part, for everybody, by way of review, want to get granular on the Empire wave. So the Empire wave is a super complicated version of the idea of a quasi-particle on that one-dimensional space moving from left to right. So in the QSN, we have these objects that we're calling helical paths that are contained in these cylindrical volumes. We can set our cylinders to be anything we want as long as they are powers of the golden ratio, right? So you can do a cylinder at phi 1, phi 2, phi 3. We can set the pitch, the distance between wafers in our Empire waves, at anything we want as long as it's a power of the golden ratio. So we have a circle, right? S1, And so the S1 is the helix, right? I mean, if I draw a circle on my chest like this, you know, there's no notion of directionality, because if you're standing behind me, it's going in one clock direction, but if you're standing in front of me, it's going in another. So there's not an absolute direction there. But if I break the symmetry and I choose to walk forward, now I'm creating a left-handed helix, and it's absolute relative to any observer. But it's still a circle. Whether I'm walking or whether I'm not walking, it's still a circle. So I'm calling it S1. So the helical component is S1. And then we're using these fifths of the 20 group, which are cube octahedra. They're groups of 4 tetrahedra, wherein their convex hull is a cube octahedron, and they have a point, a 13th point at the center, which connects to all of the other 12 points. And so we do one cube octahedron at a time. We've defined quantum clock in the past. That quantum clock definition could still stand for some upgrades in clarity. Maybe there's still some decisions of definition. But in general, the previous definition of quantum clock is that you have a set of some number of objects, and you want to have a notion of registering those objects, recognizing them, counting them. And so if we just say, I get that one, and then I get this one, and then I get this one, and then I get this one, then I call that a cycle of my set. So I can basically make it an ordered set. So I can say if this was 1, this was 3, this was 4, this was 2, and I made it go in this pattern here, then I have an ordered set of 1, 3, 2, 4. And the order within the set becomes the definition of my notion of a cycle of this clock. So it's just language I'm using to try to deliberately not use a word like time, but to just switch to order. So it's kind of trivial to say it, but it's just a language focus. So we defined a classic clock because that's just how I wanted to define it in that presentation, Quantum Clocks, Let's Get Physical, as being continuous, which continuous means if I've got these objects here and I go from this one to this one to this one, that's continuous. But if I go from this one and then go to this one and then go back to this one and this one, that's not continuous. So we could say perhaps we can think of a quantum clock, of a classic clock, as continuous, such as 1, 2, 3, 4. And we can think of a quantum clock as being discontinuous, so that as long as we cover all members of the set per cycle, we call it a cycle, whether it's continuous or whether it's out of, looks out of order or not. So then we applied empires to quantum clocks, where we said, all right, it can be out of order, and as long as it covers all members of the set per cycle, it's a tick of the clock or a cycle. And then we said, all right, if we apply empires, if I register this one here, and its empire includes this guy, so if this is a center emperor, right, which costs me money. Remember, the center emperor, I have to do some kind of mathematical action in my higher dimensional lattice. I've got to move a shift vector. I have to do some computation. So I lay down the center emperor here, and I get an empire element here. And we agreed that if the empire element covers a member of the set that's necessary to be covered in a cycle, then we've saved a computation. And so then I go to this one, and this one does not have an empire element here. So I've done this one. I have to do this one. I don't have to do that one because that's covered by an empire element. And then I have to do this one, and this one doesn't cover this one or this one or this one. So I've gotten 4 computations, let's call it, for the price of 3 by exploiting the mathematical kind of first principles of this idea of empires and center emperors. So we have our clock is these 5 orientations of the cube octahedron, right? As opposed to that square, it's more complicated, it's in 3D. It's 5 orientations of this cube octahedron where each one is oriented from the other by this golden ratio associated angle, which turns out to be the same basic angle that Fong and I discovered 10 years ago when we rotated the tetrahedra in that 5 group to get the gap to close, the 1/9. So then we've got 5 of those. So if we had a 5-fold helix on our circle, right? So I've got a 5-fold helix relative to S1 on a circle that gets extruded into a helix. And then I've got these 5 positions that fill out fifths of the Cartesian coordinates of the cube octahedron 5 compound. So if you just take the cube octahedron 5 compound and you inscribe it in a 2-sphere, then it'll make contact with a set of points on that 2-sphere, and we can write down the Cartesian coordinates of those points, those 60 points, and we can recognize that certain sets of 12 of those 60 points and their Cartesian coordinates and their spherical coordinate and their coordinates on the sphere, 2-sphere, we do those 1/5 at a time, and we call that a cycle of what we can call the spin clock, this internal Planck scale thing that's very, very small in this model of a fermion that we have. And because that's related to a 2-sphere, I'm going to write S2. And I was able to spend 20 minutes with Ray last night just convincing myself that the empire wave is a tensor product of these values that relate to the 5 on the S1 and the 5 on the S2. And I think I'll not try to take you through that, but if anybody's curious exactly why it's a tensor product, they can talk to me or Ray after. So I'm really interested in learning more about this fundamental thing here. But for now, I can tell you that if this thing were periodic, okay, you've got 5 positions on your S1 component of this pattern, and you've got 5 positions on your S2 component. It's currently under exploration, but because we're trying to exploit empire rays, like we're looking at the cylinders of volume that contain these Fibonacci chain spaced things that we call empire beams, so that we can have those empire beams cover positions in this much, much more complicated S1 cross S2 clock in the very same way that I did that on the square, where I got 1 to cover a position. And so that's the essence of the whole statistics that we're going to develop with the S-index, and we're going to allow a random number generator to make these selections when we start doing our early simulations. But the point is that if it were periodic, because like this DNA model here, if you just kind of just conceptually think about this, let's say I've got this thing where I'm trying to cover as many other positions on the opposite side of this cylinder, right? the opposite side through the axis of this cylinder, and anything down this way and over here, anywhere I can get it, I'm trying to select one of the 5 orientations of my cube octahedron that will point these laser beams of these empire rays to make as much contact with needed positions. So obviously, if I happen to be on this side of the helix, which represents being like, let's say, here, if I'm here, I'm trying to point as many beams as possible this way, and I don't care about stuff this way, right? So here, I want to point this way towards Dugan, not so much out here. And I can play around and I can say, well, I got these 5 orientations of cube octahedra that I could imagine having here, and each one of them is pointing empire beams in different ways than the other 4. So it's logical for me to assume that there's one way that might be better than the other ways. Okay, but my point is that if this were periodic, such that there is a best way, then it would kind of match up, right? Where you could say, all right, it always just repeats, right? It doesn't have to, don't worry about what I've labeled as 1 and 2 and 3 and 4. It would repeat. So if this goes to 2, right, and this goes like this, doesn't matter what it does, if it's periodic, it should repeat the pattern of matching your 5 on the helical S1 component to your 5 on the spherical cube octahedral orientations. But it's not periodic. This follows a 3-letter Fibonacci chain. So we have these 3 Dirichlet integer values for the spacing, and you can't predict where they're going to be, and you can't, it never repeats, right? It repeats in small sections, right? But it's a non-repeating, aperiodic, but highly ordered pattern, and it relates to the Binet formula. So the Binet formula is a formula that if you wanted to go to the nth Fibonacci number, let's say that the nth Fibonacci number is Fibonacci 500. Now to get to the 500th Fibonacci number by counting your way there using the recursive additive algorithm that is the Fibonacci sequence, 3 plus 5, 8 plus 5, and you keep going. To count your way there would be very computationally difficult for a big number. But the Binet algorithm allows you to dial in to any Fibonacci number without counting your way there. And that's going to become very attractive for us to try to exploit a derivative or something similar to the Binet formula in order to dial in to a random walk step that is way forward in the evolution, and we're never going to do any of this calculations or steps in between. In other words, when the random number generator picks a column in the S index, that is our analog of a measurement. And I don't think we're ever going to have the computational resources to build out the full S index for many body problems, like anything, interestingly physically realistic. Certainly not at the Planck scale of time if we tried to simulate at that level of granularity. So I'm really interested, and I'll talk more later about the idea of the Binet formula and dialing in to the nth value without knowing any of the columns in the S index before. Because for the random number generator to pick a measurement at time n, you have to give it that column. But you don't need to give it the other columns before it. If you hadn't done measurements on those columns. And now you're asking it to randomly pick according to the statistical weighting of the boxes in the column, where each box has a different savings value, and that becomes the weight with which the random number generator statistically chooses randomly. So because this will not be periodic, the statistics in our S-index columns is going to be deeply related to the Fibonacci matching rules. It's going to be related to the deepest simplified construct of a one-dimensional Fibonacci chain and what seems to be its three-letter form. So I like that because there's order in it. It becomes a series of numbers that has order. And when I see series that have order, I always ask, well, is there an algorithm or a function that can describe that order? Okay, so around this object, we have, so that picture on the wall is very beautiful. So that's the ruled surface of the relationship between the orbits of Venus and Earth. But what's so cool to me about the ruled surface over the time domain is that if you were to just take a snapshot of the relationship between Venus and Earth, it would just be a boring line, right? A distance, okay? Not a lot of interesting information. But over the time domain, it forms out the ruled surface of this complicated five-fold symmetric rosette pattern. Similarly, the empire beams themselves are very boring, like the distance as a line between Earth and Venus in a single moment. They're just these beams that come out and drop as 1 over r squared, roughly speaking. And that's an empire. And that's distinctly different than an empire wave. An empire wave is as different from an empire as that rosette pattern is different from a line as the distance between Earth and Venus. So we need to think about some sort of way of understanding that with some form of discrete calculus or however you guys are going to do that. But what I try to visualize a lot is I try to visualize the discrete calculus of what this ruled surface is like. I do my best. And I see it as a very twisty, like a bunch of twisted hop fibers. Like, you know how if you take 100 circles or hop fibers and you place them on a four-dimensional sphere. So I've taken 100 hop fibers and I've placed them evenly distributed around a 3-sphere. And then I project those 100 fibers along an axis that I like to get a good projection, and I project to 3-dimension this very complicated twisting of all of these hop fibers that has these 7 different kind of toroidal nestings. It has a distinct axis, like a tube of the torus. It has these things that go out. It has kind of some lines that are going more this way and some that are going more this way. It's very complicated and rich compared to the distribution of the 100 circles on a 3-sphere. Even though the 3-sphere is in a more complicated dimension spatially, the projection, even though it's lower, is a more complicated object because it's a product of a projection operator that's different and is not implied by the hop fiber discretized 3-sphere. So a projection is always, an irrational projection at least, is always more rich than the pre-projected object because it's a product of a projection coefficient and a pre-transformed object as another coefficient. So this thing, it looks like that to me in my visualizations where I see the S1 component first. Like I try to decompartmentalize it and I think, all right, how does the ruled surface of the helical part of these empire beams. How would that look as I integrate it over time? And I start drawing lines and arcs, and they drop that integrated field from just the S1 component. It will naturally drop in density like 1 over r squared, because the individual empire beams drop like 1 over r squared. And it will also have within it Fibonacci spacing, as well as dropping as 1 over r squared. Well, okay, so then I say, well, all right, what about the S2 component? So that's even more mind-bogglingly complicated, because it's the empire beams coming out of these cube-octahedral 4 groups, and it's rotating relative to a 2-sphere over the time, at the same time while this helical form is advancing. And how do I mentally integrate the ruled surface of the S2 component and the S1 component? And that is the ruled surface of this very complicated and rich empire wave, which is a discrete quantum field around this clock, this traveling clock. And it is the energy, it is the order within the ruled surface that defines what another empire wave experiences as energy. But it's also the energy of itself. So if you were to say, well, there are no other empire waves in the universe, it's just this one that I'm modeling in the computer. And what are the statistics of this clock's random walk? Its statistics are defined by its interaction in the future and the past with its own empire wave. Because the way savings works is it doesn't matter whether it's from a past or a future, you have to integrate it all and find the optimal savings section. So in other words, the self-interaction of our clock that defines the statistics of its probabilities of random walks is its own empire wave field, this complicated tensor product that we don't understand, that I don't understand it, certainly. I visualize it and I try to get intuitions. As I said before, I try to imagine, all right, like in a year from now, all these more geeky people than me are going to like articulate it better, learn what's possible, what's false, what's real about it. A lot of that will turn out that my imaginations were false in some cases. Sometimes I might get lucky and hit one, but the point is I try to remember what that is in the future, how you guys explain it to me, and what you show me in animations or whatever I can understand. And then I try to bumble and stumble and talk about it, right, with you guys. So when there's another one here, then its energy landscape is itself, its own interaction with its future and past ruled surface of its empire wave, plus the contribution from this one. So then in a universe with only 2 empire waves, the quantum field for the statistics of this guy's random walks are obviously the integration of this guy's discrete quantum field, its empire wave that drops in density like 1 over r squared, and the self-interaction with itself. So let's throw in some game physics suggestions. So we've got one component of this integrated ruled surface that I'm relating and labeling for now as the S1 ruled surface. And that has a binary value, right? So that has a value of chirality of right or left. Right? If it's right, the ruled surface of the empire wave is not going to be out here the same as it would be if it was left. It's different. But it's like a mirror. So whatever the frame savings or the S values, if it's a left-handed one or a right-handed one, should be pretty much similar, just with a flip of the sign value, the helicity value. So just for fun, we could call this, because it's just game physics, we could call this the charge component of the field. just in our game. And we can recognize that that charge component has something kind of more related to this direction, right? Because it's a circle with a broken symmetry in this direction, defining it as right, or a broken symmetry in this direction, defining it as left. So we want to kind of relate this portion of this integrated field more along this direction. Then we have this spherical component that's kind of just sweeping out in all directions. And maybe we can call that the magnetic component. And the magnetic component, as a conjecture, has a binary value. Because if you're on if you were on this side of this ruled surface versus being on this side, then we'll take a bathroom break soon, Ahmed, as well, if you want to gear up. So if you were on this side of this integrated object with these two components, okay, what if being on this side is different than being on this side? Now, if you look at a helix, if I just have a frozen helix, if I flip it this way to David, or if I flip it this way, there's no difference. It's still right-handed to him either way, but it looks the same to him this way or this way. But this isn't that. This is not a frozen thing. This is a really complicated ruled surface that's integrating with this S2 component, and I'm saying as a matter of, it's not exactly even as much of a conjecture as it is saying it's a thing we have to test. I have a feeling that if you're over here on this region and you're an empire wave over here, how you interact and how you see this side of this right-handed object and its integrated field will be different than this side. Why? I don't know, but there's a symmetry breaking here. That is, it's not going in both directions. It's propagating in this direction. And so maybe there's a difference in the frame savings or the savings that can interact with the particle here versus being at the same kind of position but on this side of it. If that were true and there is such a difference, then you have polarity. That we can call north-south for game terms. Okay, that's a big conjecture to explore. I don't think we can argue about it a lot. I think we have to simulate it and see what the S indices come out to. That is, what the behavior of particles, relative to it. In other words, we have to take two particles and have them face each other, flipped one way, flipped the other way. Like, we have to understand magnetism. There's another binary value, which is, let's say, remember I talked about the order of the 1, 2, 3, 4, 5 from the 2 sphere and the 1, 2, 3, 4, 5 on the circle or the helical axis. So let's say you find an ordering that is ideal. Is there a way that you could flip that ordering? So it's, in other words, what would be our game spin? So one option is that we have the opportunity, the QSN is a superposition of right 20 groups, left 20 groups. Right 4 groups and 8 groups, left. They're both there in the QSN. So if we're supposed to use both values somehow, because it is a binary value of right, left, then I wonder if we end up exploring differences where we find the optimal position of the 1, 2, 3, 4, 5s matching up with the 1, 2, 3, 4, 5s, whatever that aperiodic pattern is going to be, that's driven by the 3-letter Fibonacci chain spacing in large part. What if we were to try it, we discover a saving section and we happen to use right-handed 4 groups, right? Related to right-handed 20 groups. And we get our optimal saving section, the optimal matching of these 5 of the helical positions with these 5 of the 2-sphere, of the cube octahedral orientations. And then we say, all right, let's test it and use that same pattern, but just flip it to left. Do we have any different savings? Is the savings the same or different? I wonder. But if it were the same, then I would be tempted to call that game spin, because I'm saying for the game to start, you have to just sort of get sloppy and put your foot in the water first and just do something down and dirty and just start without taking it too seriously to just see what you can and can't do to learn. And I'm looking to learn about 3 sign values, because in the real world physics, I've got polarity, charge, and spin. And whether I like it or not, I've got 1 sign value for sure in the helicity of my helices. I might have another sign value if it turns out that my optimal saving section doesn't matter whether it's right or left. And then I might have another sign value in polarity if I find out that being on this side of the object is distinctly different from being on this side, right? Because an electron has a dipole. Is this supposed to be an electron? Is this our game electron? This has a dipole. It has a dipole, because a dipole has to have a different, this is not a dipole. This is a dipole, right? This is a dipole. A dipole has to have a difference between the 2 sides. And so this is a dipole because although it's a straight line, it has an arrow here. It's a vector. So we have a dipole in this game propagating clock.